In this video, we are going to be talking about the Carnot Vapor Power Cycle. So, what actually a power cycle is? It will produce power, okay, and by using the vapors. So, in a boiler, we add some heat. And the boiler will produce steam. The steam will hit the turbine, and we'll get some work. Okay, this is the simplest explanation for this. And what is a turbine? Turbine is a steady flow engineering device. Turbine is a steady flow engineering device, okay, that is going to follow the steady flow engineering equation, okay, and by using the steady flow engineering equation and applying some conditions on the equation, we get the work done equation for the turbine. Okay, we get the work done equation for the turbine. So that is Wt over m dot equals to h1 minus h2, and m is the kg per second. That means m is the mass flow rate. M dot is the mass flow rate. I'm sorry, m dot is the mass flow rate. So what is h1 and h2? H1 is the enthalpy, h2 is also the enthalpy, but h1 is the enthalpy before the substance has entered the turbine, and h2 is the enthalpy after it has just got the exit from the turbine. Okay, so this is how I can define the work done for the turbine. Okay, and in case of a turbine, the work done is definitely positive because turbines are meant to produce work. Okay, so now we are gonna explain it in more detail. So take a look at this. Part. Okay, so we are adding heat into the boiler. The boiler is producing steam. The steam is going into the turbine, and in the turbine, isentropic process or reversible adiabatic process will take place. Isentropic process is also named as reversible adiabatic process. Okay, so then this shaft is going to rotate, and we're going to get some work that will be further used in the power plants in order to produce energy. Okay, so after that, the steam to 3 to 4. Okay, take a look at this. This is 3 and this is 4. So from 2 to 3 we have used from 3 to 4 we have used the turbine, and from 4 to 1. Okay, take a look at this. This is 1. Okay, this is 1. So 4 to 1 we have used a condenser, and in the condenser heat is going to be rejected. Okay, so and then the rejected the steam that has lost the heat will enter the pump, and through the pump it will be sent to the boiler, and then the boiler will again heat it, and it will be a cyclic process. It will go on. Okay, the process will continue because we don't need to add heat additionally. The heat that we have, the steam that we don't need to add water additionally. The steam that we have used will be compressed by using a condenser, and then it will be again used. Okay, so let's talk about the TS diagram of for this case. So take a look at this point 2 to 3 point. Okay, let me clear it for you to understand more better. Okay, so take a look at this. Okay, so to take a look at the point 3. Okay, point 2 to 3. Okay, so from point 2 to 3 we are using a boiler, right? As we are using a boiler, what will happen is the amount of heat is going to increase. Take a look at this equation. This is the equation for the change in entropy. So dq will increase because we are adding some heat. So as dq will increase, delta S definitely is going to increase. So in this case we will see this line, right? So from 2 to 3 the entropy will increase because we are adding some heat into it, because entropy is the measurement of the randomness of a system. So as we add heat into the system, the randomness is definitely going to increase, right? So at point 3 to 4, take a look at this point 3 to 4. In between that we are using a turbine, and in a turbine we have already mentioned that isentropic process is going to take place. That means entropy will remain same, right? Entropy is going to remain same. All right, and after that we can talk about point 4 to 1. What is a bit in between point 4 to 1? Yes, that's a condenser, and condenser is taking the heat out. That means dq will decrease. Of course, as the heat will decrease, delta S is definitely going to decrease, right? So we will get a line like this. Okay, line like this. So we have seen that. Okay, so point 1 to 2 we are using a pump, and of course that is also an isentropic process. So I will get a vertical line that says that S1 is equals to S2, and in this case S3 is equals to S4, and in this case this is P3 equal to P2, and this is P4 equal to P1. Why? Because this is a constant. P4 is equals to P1 because in adiabatic process. Okay, take a look at this. we are adding the heat in a adiabatic isobaric process. Isobaric process. Have you seen that? You should notice it, but that we are adding the heat in isobaric process. Okay. So this is the all explanation for the Carnot vapor cycle, and after that we are going to move into the explanation of the thermal efficiency for the case of Carnot vapor power cycle. So this is the equation that I'm going to use. The thermal efficiency is of course network over heat added. That means the thermal efficiency is always output over the input, right? So I'm going to use, I'm going to get the value of net work. So what is the net work? Here we can see that the turbine is doing some work and the pump is also doing some work. So we need to subtract the pump work from the turbine work, right? And we have already mentioned that in case of a turbine, WT over m dot is equals to h1 minus h2, where h1 is the initial and h2 is the final enthalpy, right? So here you can see in case of a turbine, where is the turbine? Here we can see the turbine. So the point 3 is having the h3 enthalpy and point 4 having h4 enthalpy. So we need to subtract h4 from h3. So in order to get the work done for the turbine, isn't it very easy? It is very easy, right? For the work done of turbine, we are using this equation h3 minus h4. And where did this m3 disappear? Because we are doing it for a unit mass flow. That's why it is 1. Okay, because of that reason we are getting h3 minus h4. And now the rest you can very easily understand, very easily you can calculate it. I am sure that for the case of WP, that is the pump work, where is the pump? Here you can see the pump is also doing some work. So here it is having h1 and 2 stage, so I can name them, right? I can very easily name them. So let's name it h1 enthalpy, and for the case of 2 stage we can name it h2 enthalpy, right? So what you need to do now, you need to subtract h2 from h1, right? So we are doing that and we are getting the work done for the pump. We end up getting the work done for the pump. So after that we have, that means we have got the network, we have got the net work. Okay, so after that for the boiler we need the, we have added some heat. So heat added, where is the boiler? Okay, here is this. So heat added is going to be h3 minus h2, h3. So h3 minus h2 is the heat added. And then for the condenser we have also added some heat in it, so it is going to be h4 minus h1. So we have also got the heat rejected by the condenser, h4 minus h1. So now we can just substitute the values in the main equation, that is the eta for Carnot is equals to work done, that net work done divided by heat that is added. So net work done and the heat added, we have got the equation, and if we just do some calculation, we end up getting the efficiency, thermal efficiency for the Carnot heat engine. So now you may wonder that how we have got this equation, eta Carnot equal to 1 minus Q rejected divided by Q added. This is the default equation, right? And this is also an equation. If you know the value of the enthalpies, enthalpy of different points, like for the point 4.3, 0.4, 0.1 and 0.2, if you know the enthalpy, you can very easily calculate the efficiency for the case of Carnot vapor cycle. And if you know the amount of heat rejected and the amount of heat added, you can also determine the value of the efficiency of a Carnot vapor cycle.